Hi everyone, this is your next lecture. This is for section 2.1 part B. So we're going to continue talking about set theory, and we are going to continue talking a little bit about some definitions and some symbols that we need to understand. But in today's lecture, we're going to get into a little bit how some of these set theory concepts help us understand some basic mathematical concepts that we're going to be teaching. So I'm going to go ahead and start sharing my screen so you can follow along with the notes, okay? Let me get that up there for you. Okay. Here we go. All right, I think I'm gonna try to see if I can turn it like this so you guys can see it a little better. I think that's a little better, right? There we go. That looks good. All right, so as we continue in section 2.1 part B, this is starting up on page 46 of your textbook. That's what we're picking up in section 2.1. And we're starting by talking about what we mean when we say finite and infinite sets, or finite and infinite sets, however you choose to pronounce that. And these are two basically broad categories of sets, okay? So the first definition here is finite, and I'm gonna go ahead and highlight that for you, okay? So finite sets, okay, as you can see here, by definition, we define them as, and that's what I mean when I say DEF in my notes, I mean definition, is that it is when a set is empty or it has elements and all of those elements are listed, okay? And the basic common layman's terms for that is that it's where the list eventually ends. In other words, there's a very specific number of elements that could be found in that set. It does not go on forever. The list ends and we list all of them. For example, if I wanted to make the set that contains the first three letters of the alphabet, this isn't a very finite set because it would only contain letters A, B, and C, as you can see right here. So this is a finite set. These are the only three elements in it. They are all listed here. The set does not go on forever, okay? Another example of a finite set is, let's say that I wanted the set of all the even numbers between 1 and 20. Because I have definitively said I only want to go up to 20, then I could list all the even numbers that exist between 1 and 20, and that would be a finite set because the list ends and we contain all the elements in it, okay? So broad definition of a finite set. Let's move on to what we mean by an infinite set, okay? Now, an infinite set is defined, so I'm going to highlight that for you again, and here we go. It's defined with a set that goes on without end, okay? For example, if I tell you that I'm looking at, and that's what we're looking at here in this example right here, I'm looking at the set of all numbers starting with 1, well, as you and I both know, that can go on into infinity. And the way you would note it, okay, is that you would note it by putting these 3 dots that you see right there. Let me try to do a little better job of that for you. Okay, so these 3 dots right here, once you list several of the elements that would be found in the set that you've decided to talk about that is infinite, you then follow it by these 3 dots. That's how you show that the set goes on forever. It goes on without end, okay? Now, an important thing to note, and you see it right here, please note, an infinite set can be matched with a proper subset of itself. If you remember this is the symbol that we use for a proper subset, okay? And if you recall from our conversation on the last lecture video for section 2.1 part A proper subset is just a set that contains all the elements, okay, that are found in the bigger set. All of the elements in one set is found in the bigger set. Therefore, that set whose elements are all found in the bigger set is a proper subset of the bigger set, okay? So we give you an example here. For example, in this example here that you see, okay, we say that set A contains all the numbers on to infinity, and you will see that we count 1, 2, 3, 4, and then we show the 3 dots showing it goes on and on forever. Then we use the variable n, okay, to show that it continues on until infinity. That's why we use the variable n, because we don't know what that number would be. It could be any number. And then we do 3 dots after that to show that it goes on into infinity. Now, set B is all the even numbers within the set, right? This is all the numbers. Set A is all the numbers starting with 1 going on into infinity. Set B is just the even numbers starting with 2 and going on into infinity. Now, set B, again, we list a few of the numbers, then we go dot, 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 then we use the variable to show that it continues on and on and on, 2n being the case because we're talking about even numbers, and then we do dot, dot, dot again to show that it goes on into infinity. And set B, as you can see here, and I'm going to erase my sloppy little yellow arrow here so that you can see it more clearly, set B would then be considered a proper subset, hence that symbol, right? A proper subset of A, because if A contains all numbers going on to infinity, it's going to contain both all the odd and all the even numbers. But set B will only contain the even numbers, meaning that all the numbers in set B will also be found in set A. And therefore that, by definition, makes set B a proper subset of set A. Okay, so that's just an explanation of this right here. Is just an explanation of this note that any infinite set can then be, we can find proper subsets out of it. So when we have a set that is infinite, we can always find proper subsets that can come out of that infinite set. Okay. Now, moving on into the part of set theory that starts to make a little more sense to us, because it starts to sort of, in general broad strokes, explain some of the things that we know happens in math. And it's a good way to help you sort of see it from every angle so that you can better teach your students about some of these basic operations when you're teaching in elementary school, okay? And that is that we're going to talk about operations on sets, okay? Couple things to note. You need to note that sets have no elements in common. These are some terms that you should be aware of. If two sets have no elements in common, then they are called disjointed sets, okay? And here's an example. We have set ABC and we have set DEF. They have one-to-one correspondence. So as per our conversation in the first lecture of section 2.1, they would be considered equivalent sets because they have one-to-one correspondence. But they can also be called disjointed sets because they share absolutely no elements in common whatsoever, okay? On the other hand, if we have a set like we have here for example 2, where we have a set of XY, and then we have a set of YZ, this would not be a disjointed pair because they have one element in common. They both contain Y. And since they both have the element of Y, then they are not disjointed sets. That's all it takes to make two sets not disjointed. They have to have at least one element in common. So these are just two things to note, some definitions of some terminology for you to be aware of as we move forward, okay? Now let's continue talking about operations on sets. Here is the definition of operations on sets, okay? Operations are the many ways that we can construct a new set, okay? That's the important part, a new set from doing operations on two or more sets, okay? And here's why it's important, because operations can clarify our understanding of whole numbers and the operations that we do on them, okay? So the operations clarify our understanding of whole numbers and some of the things that we do with them. So let's talk about what some of these operations are. Note that every time I mention a new one, I am also showing you the symbol that you would use to represent that operation. So if we start here with A, one of the first operations we can do is perform what's called a union of sets. And this is how you would write it. Here is set A, and here is the symbol you would use. It looks like a U, okay, for union, if you want to think about it that way. So the way you would read this is the A union B, meaning you're performing a union of set A and B, okay? And the union is defined the union would be the result, okay? And that's defined as being formed by putting all the elements of set A and set B together. That's how you perform it. So when we want to perform the union of set A, wherein set A contains A and lowercase a and B, and set B, where set B contains lowercase c, d, e, the union of those two, right, A union B, would result in this set. That is always going to be the result of performing the union, is that you now have a new set. Remember our definition, right? That when you perform an operation on sets, you construct a new set, right? So when we perform the union operation on two sets, we now constructed a new set, and this new set has all the elements of A and B, and all the elements of B, C, D, and E. Okay? Let's try another example. Let me get rid of my little markings here so we can see things clearly. All right, let's look at over here at this example, example number 2. Okay? In this case, we have set A that contains the numbers 1 through 5. And we want to do the union operation with the null set. Remember, that's what this symbol stands for, the null set or the empty set. So we're going to take all the elements of set A, and we're going to perform a union with set B, which happens to be the null set or the empty set. And that means we put all those elements together. So here are all the elements of A, and because set B is the null set or the empty set, we have nothing there. So this is our answer. This is our new set that we've created by performing this union. You note that this looks very much like adding with 0, right? Okay, so now let's do this example here just because it's important for you to remember this little quirkiness about sets, all right? So here is set A. Set A is going to have elements M, N, and Q in it. We're going to perform a union with set B, excuse me, that contains sets M, N, and P in it. And recall that we don't repeat elements, so that if the element appears or occurs more than once, when we write it in the set that it belongs in, we only write it one time. So when we put all the elements of set A and all the elements of set B together into the new set that they create when we perform the union operation on them, we list M once, even though it appeared in A and in B, okay? And we list N once, even though it appeared as an element in set A and as an element in set B. And then we list Q, because remember, we're making a union, so that means we're putting all of the things together. And we list P, so that the new set created by performing the union of set A and set B is the set containing the elements M, N, P, and Q. Now, that's what reminds you here that we only write elements once, even if they repeat, right? So what you should have noticed, and I'm sure you kind of have already, is that the union of sets, so the notion of set union, is the basis for how we understand addition of whole numbers. Okay, here you kind of saw how it works when you add 0, okay? And you notice that here and here, you saw what happens when you take two things and add them together. The answer contains everything, right? Okay. Now, here's a way that you can explain how set theory, you can see more clearly how set theory really does sort of explain addition. Because here we have set A that contains two elements, elements A and B. Look at that, 2 elements. And we do the union, which we understand is analogous to addition, with set B that contains elements C, D, and E. So it has 3 elements. And when we perform that union operation, we get the new set that contains all the elements A, B, C, D, and E. And here they are, A, B, C, D, and E. That is a total of 5 elements in the new set. So we started with a set that had 2 elements, performed the union or plus a set that has 3 elements, and our answer ended up with a set that has 5 elements. Or, as we already have known since kindergarten, 2 plus 3 is 5. So you can see how there's that nice connection there with set theory, okay? Now let's talk about another operation. This operation is called the intersection of sets. And it can sound confusing because you might think to yourself, when we just think about it as words in English, intersection, union, these things have similar meanings, right? But in the term, in mathematics, when we're talking about set theory, there is something different that's happening here, okay? Here is, first of all, how you would write the notation that you would use to write the intersection. So just like we use the little U symbol for union, for intersection, it looks more like an upside down U. So this you would read this as taking the A and intersecting it, set A intersecting with set B, okay? Or you can read it as the intersection of set A and B. Now, the definition of an intersection, as you can see here, is defined as the set that is created when you perform the intersection operation is the set of all the elements that are in common to the two sets that you started with, okay? So for example, we started with set A that has elements A, B, and C. We're performing the intersection of set A with set B that has elements B, D, and F. The only element they have in common is they both have B. So therefore, the answer to the intersection of set A with set B is the set of element B, because that is the only element that set A and set B had in common. And this should remind you of how we discuss common factors. Because when we're looking at two numbers and we look at the different factors of that number, we're always looking for the ones that they have in common. And this is where that theory comes from of how we think about common factors. It comes from the operation of intersection of sets, okay? All right, let's move on. Now let's talk about the difference of sets. We already discussed how the union of sets was analogous to addition, right? So I'm sure that you can infer that the difference of sets is probably analogous to how we discuss subtraction, right? So let's talk about the difference of sets. Okay, so the difference of sets. How do we write it? Just like we would write subtraction. The difference of sets is when we have A, what looks like a minus sign, and B, but we read this as the difference between sets A and B. And the definition of it, okay, is the set, the answer that we get when we find the difference between set A and set B will be the set that has all the elements in A. Oops, sorry, we lost that there. Let's try that again. Oh, come on. It's crashing on me. Oh, don't do that. Let's try it again. Oh, let me see if I can fix what's going on here. Hold on. Let me just pause it for a second. I'm going to stop the share for a second. Okay, I think I finally fixed it. Let's try that again, shall we? All right, let's do that here. Sorry for that interruption. Hopefully this is going to work. Let's see what's going on here. There we go. All right. So we were talking about difference of sets, and we said how that's going to be sort of analogous to subtraction, just like the union of sets was analogous to addition, okay? And the difference of sets is defined as this once you find the difference of sets, you will find the set that will have all the elements that are in A that are not in B, okay? So, for example, here is set A. Okay, set A contains the elements A, B, C, and D. If we're finding the difference between that set and set B that has the elements B, C, and D, what we need to do is get rid of the elements they have in common. So they have B, C, C, and D. Therefore, the resulting set will be the set of A, because that is the element that was in A that is not in B. And remember that with set theory, order matters, and we read from left to right. So when you're finding the difference between set A and set B, you are looking for what will happen as a result of set A, or what elements are in set A that are not also in set B. Okay? So as I said, it is analogous to the notion of the difference of sets is analogous to subtraction. For example, like we did with the union of sets, let's look at this example here. We have set A that contains the elements A, B, C, and D. That's 4 elements. We are going to find the difference of that set with set B that contains the elements B, C, and D. That's 3 elements. When we get rid of the elements they have in common, B, C, and D, right, the resulting set is the set of element A, which has only 1 element. Or, as we are more accustomed to doing, 4 elements minus 3 elements is 1. Okay? So you can see how that directly applies. Finally, let's look at what we call the Cartesian product of sets. The Cartesian product of sets, as you see here, we write it this way. We write it as A cross B. And that's how you read it, okay? Before, when you had the union symbol, we read it as the union of A, B, okay? So when we had A union B, we read it as the union of A with B. If we did the intersection of A and we did the intersection with set B, we read that as the intersection of set A with set B, right? And when we do the difference of sets, and it looks like this, we are finding the difference between A and B, or the elements A has that are not in B. When we write it like this, when we're doing the cross, okay, the Cartesian product of sets, which is what this is called, we read it as A cross B. And this is defined as the set of all the ordered pairs. This is important because up until now that has not been a thing. But now when you do the cross of sets, it is a thing. Okay, it is the set, the resulting set when we take the cross of A and B is going to be the set of all the ordered pairs, and we put them in this format, A, comma, B, where, and this is the important part, where A will be an element of A and B is an element of B. Now, like I just mentioned before, order matters. It particularly matters here when we're talking about the Cartesian product, okay? And that's the note that you see here. The note says order matters, and all pairs are always first, the first element from the first set, and then second element from the second set, okay? So what does this is analogous to? We've discussed how unions were analogous to addition. The difference is analogous to subtraction. Intersections are analogous to finding a common factor. What is the cross product, or finding the Cartesian product of two sets? What is that analogous to? It is analogous to the notion or the basis from which we talk about multiplication. It's also useful when we discuss probability and geometry. Why? Because in geometry, we discuss things that have 2 points that we can plot on a graph, right? And therefore help us to see it. So let's look at this example right here before we close our lecture. If we look at the example right here, okay? Let's say that we have set A. Set A contains the elements X, Y, and Z, okay? And we want to do the Cartesian product, or the cross, with set B, which contains the elements M and N. The resulting set would be the set that contains the ordered pairs of X with M, Y with X with M, and X with N, and then Y with M and Y with N, and then Z with M and Z with N. Like the definition says, you want to put the ordered pairs of every element of A, pairing it up with an element of B. Okay, so let's do that again so that you can see it clearly. I am going to try to highlight this here for you. So we have X, and we're going to match X with the M, X with the N, okay? Then we're going to have Y, and we're going to match Y with the M, Y with the N. And then we're going to have Z here, and we're going to put Z with the M and Z with the N so that we have paired it always with an element from an element of A with an element of B. So if you see it here, and I'm going to try to make this fine pointed, there we go. Okay, you've got an A element, and then you have a B element, and then again you have A element, and then again you have a B element. Okay, so I hope that that's clear for you, because the homework is going to ask you to do some of these operations with different sets to make sure that you understand the concepts that we've discussed today as far as operations with sets. So I'm going to go ahead and stop the share. All right. The homework is going to be due on Wednesday before 1 o'clock. And Wednesday, you'll have another lecture video that's going to be up with another corresponding homework assignment. But the homework for this lecture, which officially is Monday's lecture, will be due on Wednesday by 1 o'clock. It will be found on page 52. You're going to do number 12. And then on page 53, you're going to do number 34. So it's a very short homework assignment. Hopefully you're not going to struggle with it. It's based on the definitions that we've discussed. Okay, it is already listed under the tasks. And like I said, the due date is by 1 p.m. on Wednesday is when this homework assignment will be due. And again, thank you to those of you who resubmitted your homework assignments from section 1.1. As you saw in the message that I posted, there was some technical difficulties, and I had graded through all of them or most of them, and then they just disappeared, both off of my grade book on Blackboard and then apparently from your end as well, because I was alerted to that when a few of you emailed me saying, hey, my work disappeared and I had already submitted it, and now I don't know what happened. So I'm not really sure what went down there, but a lot of you have already started to resubmit, so thank you for that. My apologies. You will not be counted late. Just make sure that I get all those assignments turned in, as well as the ones that were due by 1 p.m. Monday, so that I can have those all graded for you in time for Wednesday. All right. Have a wonderful day.